how do we know that that carbon dioxide is of anthropogenic origin? Well, we have several ways of getting at that information. First of all, fossil fuels are commercial quantities. They're things we buy and sell. So we know how much of them we're selling very accurately. We know how much we're burning. We know how much we're putting in our cars. We have a pretty good sense of how much carbon dioxide got produced from the fossil fuels that we bought and burned. And consequently, we can keep track pretty accurately of how much carbon should have gone into the atmosphere from the fossil fuels that we burned at any given year. Now remember that only about half the carbon we emit from our tailpipes and smokestacks and so on ends up staying in the atmosphere, but we understand that also, even if we don't know exactly how that carbon is getting partitioned among the soils and the oceans that are taking them up. So we have a good measure. If you tell me you burn a barrel of oil, I can tell you how much the carbon dioxide content of the atmosphere ought to go up. And the measured industrial era rise in atmospheric CO2 correlates with, in fact, our measured quantities of this commercial commodity fossil fuel that we've been burning. So that's one way we know this well. Another way is more scientific and a little more subtle. Carbon, like plenty of other elements, comes in different isotopes, and there are three particularly interesting isotopes of carbon. Most of the carbon is carbon-12. It has 6 protons and 6 neutrons in its nucleus. That's the common kind of carbon. There's another isotope of carbon that's also stable, constitutes much less of natural carbon, and that's carbon-13, which has an extra neutron in its nucleus. Then there's an isotope called carbon-14, which you may have heard of. It's a radioactive isotope. It only lasts about 5,000 years before it decays away, and it's created continuously in the atmosphere by cosmic rays. And that's what's used in radiocarbon dating, incidentally. Well, that means atmospheric carbon dioxide is a mix of carbon-12, carbon-13, and carbon-14. A very small amount of carbon-14, but it's easy to measure it because it's radioactive. The carbon in fossil fuels has been buried in the ground for millions, tens of millions, hundreds of millions of years. Any carbon-14 that was in it has long since decayed. So it should be depleted in carbon-14. Furthermore, the plants that originally did the photosynthesis preferentially take up the lighter isotope carbon-12, and so fossil fuels are also depleted in the stable isotope carbon-13. And as we look at the isotopic content of the atmosphere, that is, what the ratio of carbon-12 is to the other 2 carbon isotopes, we find that over time, isotopically, the carbon content of the atmosphere has become more and more depleted in carbon-13 and carbon-14. Why? Because we're putting into the atmosphere extra carbon, and the carbon is coming from a place where it had time to decay away its carbon-14 and where it didn't have as much carbon-13. And so the atmospheric carbon content is being reduced, depleted in carbon-13 and carbon-14, and that tells us that we're dealing here with carbon that was coming from deep within the Earth, particularly from the fossil fuels. Finally, one other measurement is telling us that the oxygen content of the atmosphere is decreasing in a way that's consistent with our combining extra oxygen with carbon as we do when we burn the fossil fuels and make carbon dioxide. Now, you don't have to worry that you're about to suffocate. It's a subtle change, but it's a very clear and measurable change, and it too is consistent with the depletion of, or with the addition of carbon to the atmosphere from the fossil fuel resource. So I think it's incontrovertible that the carbon dioxide content of the atmosphere has increased significantly during the industrial era by something on the order of 30 to 40%, and it's also uncontroversial that that rise is a result of our burning, largely a result of our burning fossil fuels, which have been buried in the ground for tens to hundreds of millions of years. So we know we have anthropogenic carbon in the atmosphere, and it's a significant rise in atmospheric carbon dioxide. But how unusual is the rise of approximately 30 to 40% over a period of 250 years or so of the industrial era in terms of the context of historic carbon dioxide? Well, one thing I would remind you of is that we asked that same question for temperature, and for temperature we found that the temperature increase of the last few decades at least is unprecedented, at least on the millennial timescale, going back 1,000 years. If you were to consider overlaying our CO2 records for the past 1,000 years, and we can go back 1,000 years, and what you would see is CO2 was roughly level at that pre-industrial 280 parts per million approximately, and then about 1750 it started rising, and it took a very steep rise, the rise getting steeper and steeper as we get into the 20th century and into the 21st century, that rise culminating in today's level of about 390 parts per million. So you would see essentially a level for most of the first part of the millennium, and then starting with the industrial era, a gradual upturn that gets steeper and steeper and steeper at the end. That's what a graph of CO2 over the millennium would look like. It looks a lot like those temperature curves from those millennial temperature reconstructions that I showed you earlier. They showed a slight decline in temperature for roughly the first 900 years of the millennium, and then a steep upturn at the end. If you were to imagine overlaying those temperature reconstructions on the CO2 curve, the millennial CO2 curve, you would see quite a remarkable correlation in those two curves. The CO2 rise at the end, during the industrial era corresponds with that steep rise in temperature at the end of the millennial temperature reconstructions. What if we go further back? Well, I already showed you the results of going further back with carbon dioxide measurements. I had correlated them with temperatures, and I want to take another look at that. So I'm going to show you a graph, which is one that we've seen before, but I want to do one additional thing to it. I want to add the industrial era carbon dioxide rise to that graph. And this, to me, is one of the most significant indications that we humans have done something substantial to the natural system of the atmosphere. So let's take a look at what happens with 400,000 years of carbon dioxide from that Vostok ice core record. We remember that that correlated very nicely with the temperature. So when we put those two graphs on top of each other, they look almost the same. That's that correlation between temperature rise and CO2 concentration. We saw that 6 degrees Celsius difference between the temperature today, roughly, and the temperature in an ice age. We saw that cyclic 100,000 year pattern with short interglacial periods of relative warm temperatures separated by long, cold ice ages when the climate was a lot cooler than it was today. And by the way, the carbon dioxide level was down much lower at somewhere around 140, 150 parts per million, much lower than it is today. A little below 200 parts per million, I guess. But if you add the present day carbon dioxide concentration to that graph, and that's what I've done in the graph we're looking at here, we add that up to 390 parts per million, that addition looks like just a vertical spike at the end of the 400,000 year temperature and CO2 record. A vertical spike, a rise in carbon dioxide to levels that the planet has clearly not seen in about 500,000 years. Way above anything the planet has seen in 500,000 years. About 30% above any carbon dioxide level Earth has seen in 500,000 years. Our newest ice core data take that back about 1 million years, so we can say with confidence that we have added to the atmospheric CO2, bringing it up to levels that are substantially higher than anything the planet has seen for 1 million years. And we have less direct evidence, but still good evidence, that probably the levels of CO2 in the atmosphere today are higher by a substantial amount, something like 30%, than they've been any time in the last 20 million years. And to me, that's the biggest indication, again, that we human beings have altered the atmosphere system, the Earth atmosphere system, which is a major part of the climate system, in a way that is substantial and unprecedented. So we're looking at a rise in atmospheric CO2 to levels that the planet has not seen for at least 1 million years, and probably 20 million years, to levels that are well above anything it's seen in those time intervals. That's a big deal. And I think that's the clearest indication of a human influence on climate, or a human influence on atmospheric composition, which ought to cause a human influence on climate. Now, carbon dioxide is not the only thing that we do, put in the atmosphere, that changes climate. There are a number of other human activities that change climate, and I want to look briefly at them, some other human influences on basically Earth's energy balance, because anything that upsets that energy balance will change the climate. And I want to run quickly through these, and as I describe these, think about what it would look like if one were to draw a graph of them. Some of these influences cause a positive upset in the Earth's energy balance. It makes it seem like more energy is coming in or less energy is going out. It's the same thing either way. And that's called a forcing, and a positive forcing like that corresponds to an increase in temperature, or would cause an increase in temperature. Other things we do may alter the Earth's climate in a way that causes cooling. And we can describe those by imagining a bar that extends from 0 downward to some negative forcing value. And those forcing values are measured in watts per square meter. How much is the energy balance on every square meter at the top of the atmosphere or at the stratosphere, troposphere boundary? How much is that energy flow balance upset by these different phenomena? And if we look at them,